a road map. Junctions joined by roads, each road with a length. A task pipeline, where some jobs must finish before others begin. Both are the same object, a graph. And here's ours on the right. 6 vertices, and every edge carries a weight. 3 questions run almost every real network. What is the shortest route between 2 points? What is the cheapest set of connections that still ties the whole thing together? And in what order can I run tasks? So nothing starts before what it depends on. 3 questions. 3 classic algorithms. Shortest paths. With breadth first search and Dijkstra's algorithm. The minimum spanning tree. And topological sort. By the end, you'll watch each one run on this very graph. Start with the simplest version. Forget the weights for a moment and just ask, what's the fewest edges from a start vertex to every other? When all edges count the same, breadth first search answers it perfectly. Grow outward from A in rings. Level 0 is A itself, distance 0. One step out. The neighbors of A, B and C, both at distance 1. 2 steps out. The new vertices reachable from that ring. D and E, both distance 2. And 3 steps out. F, the last vertex, at distance 3. That's the whole idea. The first time breadth first search reaches a vertex, it's by the fewest possible edges. Fast, order V plus E. But notice, it counts edges, not weights. The moment roads have different lengths, fewest edges is no longer shortest distance. For that, we need something cleverer. Dijkstra's algorithm is the centerpiece of shortest paths, and its idea is wonderfully simple. Keep a running best guess, a tentative distance to every vertex. 0 at the source, because you're already there. Infinity everywhere else, because you haven't found a route yet. Then repeat 3 moves. Pick the unvisited vertex whose tentative distance is smallest. Settle it, lock that distance in as final, because nothing can reach it more cheaply now. And relax each of its edges. And here's what relax means, in one line. For an edge from U to V, check whether going through U, that's US distance plus the edge weight, beats V's current best. If it does, update V. If it doesn't, leave V alone. Relax is not always update. It's update only when you've genuinely found something shorter. One condition makes this whole greedy trick work. Every weight must be non-negative. No negative edges. Keep that in your back pocket. It comes back as the number one trap. Let's run it from A. Every distance starts at infinity, except A at 0. Watch the table on the right update as the graph settles, vertex by vertex. Smallest unvisited distance is A at 0. Settle it. Color it green, it's done. Now relax A's edges. A 2B costs 2, so B's distance becomes 2. A 2C costs 5, so C becomes 5. Next smallest is B at 2. Settle B. Relax its edges. And here's the moment that makes Dijkstra shine. B to C costs 1, so through B, C would be 2 plus 1, 3. That beats C's old 5, so we relax it. C drops to 3. B to D costs 7, giving D a first value of 9. Now the smallest unvisited is C at 3, the improved value. Settle C. Its one useful edge, C2E, costs 3. So E becomes 3 plus 3, 6. Smallest left is E at 6. Settle it? E to D would be 6 plus 4, 10. But D already sits at 9, so we do not update. That's relaxation refusing to make things worse. E to F costs 6, so F becomes 12. Only D and F remain. Settle D at 9. Its neighbors are already done. Then settle F at 12. Every vertex is green. The algorithm is finished. And there's the answer table. From A, B is 2, C is 3, D is 9, E is 6, and F is 12. Each one is the true shortest distance. For instance, the shortest route to F runs A, B, C, E, F, and the lengths add to 12. Here's Dijakstra in a dozen lines. Start every distance at infinity, the source at 0, and push the source into a min heap, a priority queue that always hands back the smallest distance first. The loop pops the closest unsettled vertex, marks it done. That's the settle step, then walks its neighbors. And this is the heart of it, the relaxation. If reaching V through U is shorter than Vs current best, lower Vs distance and push the better value back into the heap. Every edge is relaxed once. The heap keeps the order right. With a heap, the whole thing runs in order V plus E times log V, fast enough for road networks with millions of junctions. If negative weights are possible instead, you'd swap in the Bell-Manford algorithm. Second question, a different goal. Forget one source. Now connect every vertex together, using as little total edge weight as possible, with no redundant loops. That's the minimum spanning tree. We'll grow it with Prim's algorithm. Start anywhere, say A, and keep one rule. At each step, add the cheapest edge that leaves the tree and reaches a brand new vertex. A running total tracks the weight. The cheapest edge out of A is A, B, weight 2. Added B joins the tree, total 2. Now the cheapest edge leaving A or B into a new vertex is BC, weight 1. Add it. C joins, total 3. Cheapest edge out of the tree now is CE, weight 3. E joins, total 6. From the tree, the cheapest new edge is ED, weight 4. D joins, total 10. Notice we skipped BD at 7. ED is cheaper. Finally, only F is left. It's only edge EF, weight 6, brings it in. Total 16, and all 6 vertices are connected. What about the 2 edges we never used? A, C at 5 and BD at 7. Add either one and it would close a loop, a cycle, giving a second path between vertices already connected. A tree forbids that, so both are rejected. 5 edges, 6 vertices, always one fewer edge than vertices for any spanning tree. Total weight 16, the smallest possible. And greed works here for a deep reason called the cut property. The cheapest edge crossing out of your tree is always safe to take. Here's a trap that catches almost everyone. The shortest path tree and the minimum spanning tree look similar, but they answer different questions. And on the very same graph, they can differ. Let me put them side by side. On the left, the shortest path tree. The edges Dijakstra used to reach every vertex from A as cheaply as possible. To get to D fastest, it goes A, B, D, using the edge B, D of weight 7. On the right, the minimum spanning tree, smallest total wiring. It does not care about A at all. It reaches D through the cheaper edge D, E of weight 4, and drops B, D entirely. They differ by exactly one edge. The shortest path tree spends 7 on BD to keep A's route short. The spanning tree spends 4 on D, E to keep the total low. 19 versus 16. Same graph, 2 different best answers. Never conflate them. Last question, and a different kind of graph directed. Think of a data pipeline. Collect the data, clean it, build features, train, evaluate, report. An arrow from one task to another means the first must finish before the second can start. It has no directed cycle. You can never loop back to a task you already did. A directed graph with no cycles is a DAG. And for a DAG, we can list every vertex so that all arrows point forward. That listing is a topological order. Kahan's algorithm makes it concrete. For each vertex, count its in degree. How many arrows point in? Collect. Nobody points at it. In degree 0. Everything else has 1 or 2 prerequisites still pending. Start with the in degree 0 vertices. Just peel it off. Add A to the order and remove its outgoing arrows. That drops B and C 2 0. Now B and C are ready. Take B next. Removing BS arrow drops D from 2 down to 1. Not ready yet. Take C. Its arrows into D and E drop D to 0 and E from 2 to 1. D is now ready. D comes off. Its arrow into E drops E to 0. E is ready. E comes off and its arrow drops F to 0. And finally, F every vertex is placed. The order is A, B, C, D, E, F. And every arrow in the graph points from earlier to later. That's a valid topological order. It isn't unique. Had we picked C before B, that would work too. Only the arrows constrain what must come first. One catch. A topological order exists only if the graph truly is a DAG. Sneak in a single back arrow, say from evaluate back to features, and you've made a cycle. Now no ordering can put every arrow forward. Kahan's algorithm detects it. It stalls, unable to place every vertex, and that's your proof a cycle exists. Your turn, and it's a good one to end the whole data structures journey on. Same weighted graph on the right. Using Dijakstra from A, what is the shortest distance all the way to E? Pause the video, work it through, and find both the number and the root. I'll wait. Here's the walkthrough. The direct edge A to C costs 5, but going A-B is only 2, and B to C adds 1, reaching C in 3. That's the relaxation win. Then C2E adds 3 more. So the shortest distance to E is 6. Along ABCE, not the direct looking route. 6 by way of B and C. If you got that and saw why the cheap looking direct edge loses to the 2-hop path, you've genuinely understood how Dijakstra relaxes its way to the truth. Beautifully done. Trap 1. The big one. Dijakstra assumes every weight is non-negative. Add a negative edge and its greedy settling can lock in a distance that a later negative shortcut would have beaten. For negative weights, reach for Bell-Manford. Trap 2, which we just saw. The shortest path tree minimizes distance from one source. The spanning tree minimizes total wiring. They often differ. Solving one does not solve the other. Trap 3. Topological sort only exists for a directed acyclic graph. One cycle and there is no valid order. And if Kahan's algorithm can't place every vertex, that's exactly how you detect the cycle. And trap 4. 2 habits to keep straight. Relaxing an edge updates a distance only when the new route is genuinely shorter, never blindly. And building an MST greedily still means refusing any edge that would close a cycle. Let's bring it all home. For shortest paths, breadth-first search handles the unweighted case in order V plus E, and Dijakstra handles weights in order V plus E times log V. Dijakstra is just 2 moves on repeat. Settle the closest unvisited vertex, then relax its edges, updating a neighbor only when you found something shorter. It needs non-negative weights. The minimum spanning tree connects everything with the least total weight. Grow it greedily with prim or criscal, never forming a cycle, ending with one fewer edge than vertices. And topological sort orders a DAG so every arrow points forward, by repeatedly peeling off the vertices with nothing left pointing at them. Master shortest paths, spanning trees, and topological order, and you can reason about almost any network you'll ever meet. That completes our tour of data structures and algorithms.